Swayam Prabha. Digital India. Educated India.
Dear friends, a very good day to all of you and welcome to this video lecture on principles of engineering system design. This is the first lecture on this series of lectures on system design, and in this lecture I will introduce the topic and discuss about what are the contents we are going to discuss in this lecture. System design or engineering system design may be a totally new topic to some of you, or to some of you, you may be wondering what is system engineering and what are the topics we are going to cover in this lecture. And most of you might have used the system or heard about system engineering in various contexts. We talk about various systems, we talk about democratic system, we talk about education system, we talk about the human body as a system, and there are many other systems. We talk about electoral systems, and then we talk about even IIT as a system. So what actually we mean by system when we discuss these various systems which is around all of us. A system basically is a set of entities when put together gives a desired output. Engineering system is also something similar to that. There are various entities. There are human beings in the system, there are machines, there are materials, there are mechanisms, there are computers, softwares, there are a lot of interfaces, hardware. There are so many entities in the system, and when we put together all these entities and put them in such a way that we get a desired output. So engineering system is basically a collection of various entities when put together gives you a desired output. So here also in this course, in engineering system design course, we are trying to see how do we actually identify the entities needed for a particular output, how do we put them together, and how do we actually make sure that these entities put together gives us a desired system. So the focus of this course is basically to understand the principles on which the system design is focused or system design is based upon, and then how do we actually do a systematic way of designing the engineering systems in order to make sure that it actually produces the desired outputs. Most of you must be knowing about the various engineering systems existing. In this course, we will be focusing on complex engineering systems where actually the magnitude of the number of components, the number of entities or the number of subsystem involved is huge. Therefore, we need to have a very systematic process of designing the system, and that is the focus of this course, engineering system design. Sometimes engineering system design refer it as systems engineering, and this is very common to other fields also. It is not only to engineering field. We can see that systems engineering is applied in various other social sciences also. We talk about systems engineering, and the focus of this course is basically to look at the engineering aspects or the engineering systems and how do we design the engineering system. Let us look at what is system engineering or why do we need systems engineering. As we know that most of these engineering systems are there already, and we have many natural systems or man-made systems, but then why do we need to have a very focused engineering system design approach? If we look at some of the case studies from the history, we can see that there are a lot of failures in the engineering systems, and this actually led to the development of system engineering as a separate discipline, and therefore we need to have a systematic approach for designing systems, because a systematic approach will reduce the errors and reduce the failures of the engineering systems and ensure that it actually produces the desired outputs. Look at the picture in this slide. You can see this is an airbag system which most of the automobiles are having. Modern automobile vehicles have this kind of airbags as a protection device for passengers as well as drivers. But when these devices were introduced in early 1990s, this actually the safety device itself became a cause of death for a noticeable number of individuals. though that was not the intention of the airbags. The intention of airbags was to protect the people, but because of some design failures or the system failures, this became a cause of death for many individuals because of the malfunctioning of the airbag. If you look at the reasons for it, we can see that there were many flaws in the design, testing and deployment conditions envisaged in the system design. So, one of the main reasons for the failure was flaws in the design, testing and deployment conditions. So, that actually tells us that it is necessary to find out the actual requirements of the system, and once we have the actual requirements of the system identified, we need to ensure that these requirements are actually implemented in the system, or the functions needed to meet these requirements are implemented and they are tested and verified fully before we really implement the system for the actual application. So, this was the one of the reasons for the failure of this airbag system. Like this, we can see a lot of examples. Ariane 5 flight 501 failure, again this is a case of system failure. You can see this Ariane 5, the launch vehicle developed by European Space Agency, was first launched on June 4, 1996 with 4 satellites on board. At 37 seconds into flight, Ariane 5 veered off course and disintegrated shortly thereafter. Again, this is a failure from the history, engineering failure of the system. As you know, this is a very complex system. All the launch vehicles are basically very complex engineering systems, and again this had some flaws in the interfaces. The design interfaces were not proper, so there were some flaws in the conversion of the data, and this actually led to the failure of the this particular system. So, a major flaw in the communication interface resulted into this catastrophe. So, again it actually emphasized the importance of having a systematic approach in the design and development of engineering system, because there are many subsystems and there are multiple interfaces, and if interfaces are not properly designed, then that may result into a tragedy like this. This is another example which is very famous, and most of you may be aware of it, the Columbia disaster. Again the space shuttle Columbia, when it was returning back to the earth after its mission, disintegrated into pieces, and all the astronauts were killed in this particular incident. This actually happened in 2003, February 1, 2003. In fact, these are the crew members who actually died during the return of the space shuttle, and as you know, one of India's daughters also lost her life in this particular mishap. If you look at the details of this particular incident, we can see that this particular incident happened because there was a small problem and the space shuttle took off. One of the tiles on its surface developed some cracks, and it was an issue which actually mission managers, they identified in the beginning itself. When it took off, they could see that there is a problem with the one of the tiles on the surface. But then it was not possible to bring it back immediately, so they did lot of analysis, they did modeling analysis and lot of simulations to see what are the consequences of this particular damage. And finally, after a lot of analysis and a lot of studies, and then they took a decision that this may not cause a major problem, so that they can continue with the mission and then return the space shuttle back to earth and then do the repair work. So, here actually it was a decision making under uncertain conditions. So, it was not sure, I mean the team was not very sure whether the system will perform as per their simulations, but they need to take a decision under a lot of other uncertain conditions, and they took the decision to continue with the flight. And then while coming back, while the shuttle was returning back, the temperature rose up very high, and then it actually resulted into the complete failure of the system. The whole space shuttle and all the crew were killed in the accident. So, here you can see that it is not only the engineering aspect, but there are so many other aspects like making a particular decision about whether to continue with the system mission or not. So, we need to consider so many other aspects of the system and then take a decision under a lot of uncertainties. So, taking a decision under very uncertain conditions also is part of system engineering. So, here all these incidences basically tells us that engineering a complex system is very difficult, and there are a lot of issues need to be taken into account when we actually design and develop and deploy an engineering system. To show the level of complexities, you can take this example for the ICBM project, which is the Intercontinental Ballistic Missile Project Atlas. The Atlas had a lot of various steps involved in this development of this particular missile shield system. So, SM-65 was the missile designed by the Air Force Ballistic Missile Division and built by a conveyor division of General Dynamics. This was originally designed as an ICBM in the late 1950s, and Atlas was the foundation for a family of successful space launch vehicles now built by United Launch Alliance. The Atlas rocket family is today used as a launch platform for commercial and military satellites and other space vehicles. So, this actually got a series of launch vehicles. The present one is it was built around 2002 or 2003, but the development started somewhere in 1950s, and then it actually there were various versions of this particular program, a missile. To see the complexity of this development, you can see that there were 18,000 scientists and engineers working in this particular project. There were 17 contractors, there were 200 subcontractors and 200,000 suppliers involved in this particular project. So, you can actually imagine the scale of the project with the 18,000 scientists and 20,000 suppliers, and in between lot of contractors and subcontractors working together in order to deliver a particular project. So, the management of the whole manpower, the subsystems, the interfaces, all this becomes too complex for anyone to manage the system. This actually shows the evolution of the Atlas family. You can see that started somewhere in 92 with the first version of this product, Atlas 2A, and then Atlas 5 is the latest one. It is basically Atlas 5 family consists of these 3 series, and it was final one was developed in 2002. You can see that as the development progresses, there will be a lot of additions, lot of changes in this system, and every time somebody has to closely monitor the variations in the system design and closely record it, and then maintain a proper strategy for the development also. So, all this makes the system development very complex and requires a very systematic approach in the design development as well as deployment and even the disposal of the system. So, let us see what are the important points we need to discuss or we need to learn when we design this kind of complex engineering systems. To define the system engineering, basically it is a top down life cycle approach to the design, development and deployment of large scale systems, processes or operations to meet the effective needs of users and stakeholders in a cost effective, high quality way. So, as you can see, it is a top down life cycle approach. So, it is not only the design which is important. So, we need to look at the whole life cycle of the system, where we look at the design, the development, the deployment and even the training and maintenance of the system, and then how do we actually dispose the whole system. So, it actually a life cycle approach where we need to look at all aspects of the life cycle of the system, and then every life cycle need to be analyzed and we need to make proper design for these life cycles. When we design a system, we need to even look at how do we actually finally dispose the system. Is it going to affect the other existing systems or natural systems, or can we use it for some other system, or can upgrade the system further. So, all these aspects need to be taken into account when we actually go for the design of this type of a complex engineering system. So, system engineering is basically an organized and systematic way of design, and then it considers all the factors involved in the design. So, it is not only a particular aspect of the system. So, we need to look at all the aspects of the design. So, looking from the customer requirements to the disposal of the system, everything need to be designed, that is all the factors need to be considered, and then it integrates all the disciplines and specialty groups into a team effort. So, here actually you will have multiple disciplines. So, it is not only a particular discipline in engineering, there will be multiple specialty groups, and this actually tries to integrate them into a team effort, and it ensures the business and customer needs of all stakeholders and ensures a system that meets the user needs. So, here actually the business needs as well as the customer needs of all stakeholders. There are multiple stakeholders in the system development. So, we need to ensure that we take care of the stakeholders' interest and meet their needs of these stakeholders. So, what are the things what we are going to discuss in this particular lecture? We will see the topics to be covered in this particular course. we have around 30 to 40 lectures on systems engineering or principles of engineering system design. So, the main topics to be covered in these lectures are first basically the introduction to system engineering, and then we discuss about the system engineering design process. So, what are the different life cycles in a system and what are the different product development processes we can employ, and then we go through the 6 functions of a design process. Basically we will define the system level design problem, then functional architecture of the system, then physical architecture. Basically the functional architecture will look at the functions needed in the system in order to satisfy the customer requirements which are identified in the system level design problem, and then we go to the physical architecture, where the physical architecture will try to convert the functions into physical building blocks, and then we develop an operational architecture which actually integrates all the physical architecture. Then we develop the interface architecture basically to look at the subsystems and the interfaces needed for these subsystems, and finally we do the integration and qualification. So, that is the last function in the design process. Whatever we design, we to do an integration of all the subsystems and then ensure that the systems or the subsystems meet the requirement of the stakeholders. So, that is the qualification process where we do the testing and analysis of the whole system and ensure that it actually meets the customer requirements, and once it is verified, then only it will be used for customer application or for the further development of the system. So, these are the 6 functions of the design process. Our main focus will be on these 6 functions. We will try to understand how do we actually carry out these functions in the design process across the life cycle, and then we go to the other topics such as system failure analysis. So, we will look at the failure analysis of the system and then see how do we actually design a system in order to make sure that the possibility of failure is very minimal. We discuss about the decision making under uncertainty, where we look at the various options available or various techniques available in order to take a decision based on the available information at that time. So, there is a risk involved in the decision making. So, we will see how do we actually reduce the risk involved in the decision making process, and then we will discuss about a few system modeling tools, because we have to do a lot of analysis while we design the engineering system. So, we will discuss about a few tools available for modeling of the system. And similarly, we will look at the statistical tools for engineering design, basically the design of experiments and design for reliability, etc. There are few software tools available for system design. So, I will briefly explain about these tools and how do we use these softwares for effective design of engineering systems. And of course, I will take few case studies and examples to show how to use these tools as well as these methods in the design of system as well as the implementation of the system, and then to see how the principles of a systematic process actually helps us to design complex systems and ensure that it actually meets the customer requirement. So, these are the main topics which will be covered during these lectures. Maybe 30 to 40 lectures will be there, which actually will cover all these topics and few case studies also. Some of the references for this lecture: the textbook is Dennis Bute, The Engineering Design of Systems. Then another book by Alexander Kosayev and William Sweet, Systems Engineering Principles and Practice. Then Saeed Niku, Creative Design of Products and Systems, Wiley 2009 edition. Apart from this, I will be giving you a few assignments and group projects. The assignments will be uploaded to the web, and then you can actually try it yourself. Some of the answers for these assignments also will be given in the web itself. You can actually refer to that and then see whether you are actually doing it properly, or you are actually understanding the principles and then how to apply these principles for the design of complex systems. There will be few group projects also. Of course, these group projects you can actually, if you are in a group or 3 or 4 students together, you can work out these projects and then try to see how to implement or how to use the principles in a real life scenario or real case studies. So, that also you can try as part of the course. So, the main course objectives, what we actually can see from after at the end of this course, we have some objectives in providing these course materials to you. So, at the end of this course, you should be able to develop a systems engineering plan for a project and judge the applicability of any proposed process, strategy or methodology for systems engineering. So, you should be able to plan a project in terms of systems engineering and then judge the applicability of any proposed process for this particular project and apply the most essential systems engineering tools to realistic problems. So, if you have a realistic problem, how do we actually apply the most essential systems, so that also you should be able to understand by the end of this course, and then recognize the value and limitations of modeling and simulation. We will be discussing about many simulation and modeling techniques. So, you will be able to recognize the value and limitations of these models and formulate an effective plan for gathering and using data, and how do we actually gather data and use them in the design, and then determine the effects of manufacture, maintenance and disposal on system cost and value. So, you should be able to determine the effects of cost on various aspects like manufacture, maintenance and disposal on system. So, there are different various costs involved in this. So, you should be able to understand the impact of this on the system design. So, these are the course objectives. So, what we mentioned so far is the introduction, and then what are the topics to be covered in this course and what are course objectives. And now we will go to discuss more about the systems engineering, and we will try to define the systems engineering from the design point of view, from the engineering perspective. We will design what is system, what is engineering, and what is system engineering, and what are the roles of system engineers in developing this kind of complex systems. So, let us look at what is the definition for engineering, because systems engineering is basically, you can say that there is a system and there is engineering. So, we will discuss what is engineering and what is system, and then what is this system engineering. There are a lot of definitions for engineering, but basically if you look at engineering is a process of doing things in an effective way. Even without engineering or without a proper definition for engineering projects were taking place, people were doing it, because whenever you try to do something in a cost effective and an efficient manner, then we call it as engineering. As Arthur Wellington said once, engineering is the art of doing something well with $1 which any bungler can do with $2. So, basically we are trying to do how do we do it in an efficient way with using the known principles and practices. How do we complete a project in a cost effective and an efficient way? That is basically the engineering. But there are different definitions. So, as per the accreditation board for engineering and technology, engineering is the process of devising a system, component or process to meet desired needs. So, basically it is a process of devising a system, component or process to meet the desired needs. It is a decision making process, often iterative, in which the basic sciences, mathematics and engineering sciences are applied to convert resources optimally to meet a stated objective. So, here an optimal utilization of the resources to meet a stated objective is defined as engineering. Then what is a system? So, we discussed about a system, or we briefly mentioned about systems. Basically there are various systems existing in the nature. There are man-made systems, artificial systems are there. So, how do we actually define a system? There are various definitions for system. A system is defined as a group of interacting, interrelated or interdependent elements forming a complex whole. So, that is one of the definitions. The other one is a functionally related group of elements, like the human body regarded as a functional physiological unit, or an organism as a whole, especially with regard to its vital processes or functions. The other definition is a group of physiologically or anatomically complementary organs or parts, like the nervous system or the skeletal system. So, these are actually a physiologically or anatomically complementary systems. A group of interacting mechanical or electrical components, or a network of related computer software, hardware and data transmission devices. So, if you took internet as a system, then again it is a network of related computer software, hardware and data transmission devices. So, like this there are multiple definitions. Standard definition is basically a system is commonly defined to be a collection of hardware, software, people, facilities and procedures organized to accomplish some common objective. So, that is a a common definition for engineering system, which is a collection of hardware, software, people and other facilities in order to get to accomplish a common objective. NASA Systems Engineering Handbook, the definition for a system is given as a set of interrelated components which interact with one another in an organized fashion toward a common purpose. So, that was the definition given by the NASA Systems Engineering Handbook for an engineering system, and it actually contains many components. So, there can be very diverse components in the engineering system. There can be persons and organizations, there can be software and data, there can be equipment and hardware, facilities and materials, and services and techniques. So, you can see they are quite diverse: persons and organizations, software, data, equipment or hardware, and facilities and materials, services and techniques. So, this can be any system can have any of these components. Some of them may be having all these components, or some of them having few of these components, but any system will be having very diverse components in order to meet the requirements. As per the NASA System Engineering Handbook, system engineering is a robust approach to the design, creation and operation of system. So, it is not only the design activity, it is basically an approach to the design, creation and operation of systems, and it consists of identification and quantification of system goals. So, these are the approach for the system design. We need to look into these aspects like the identification and quantification of system goals, creation of alternative system design concepts, performance of design traits, that is there may be many design trade off in the system, because when we design a system we will be looking at the aspects of trade off, where we need to reduce the cost sometimes or increase the performance, or when you try to increase the performance the cost may go up. So, we need to have some kind of a trade off, and that kind of trade studies are also part of the system engineering. So, that actually is the design trades. Then we have the selection and implementation of the best design, that is the balanced and robust design, and then we have verification that the design is actually built and properly integrated in accordance with the specifications. Then assessment of how well the system meets the goals. So, these are the important steps involved in the system engineering or design of engineering systems. So, we look at the system goals, then the design concepts, then trade off, then the verification strategies, and then assessment of how well the system performs as per the or to meet the stakeholder needs. These are the things important in the design of systems. So, that is about the system, and then we discussed about engineering also. Then what is systems engineering? So, we have the system, which is a collection of entities which actually provides you a particular output, and then in systems engineering, which again we briefly saw this in the earlier slides, system engineering is a top down life cycle approach to the design, development and deployment of large scale systems, processes or operations to meet the effective needs of users and stakeholders in a cost effective, high quality way. So, it actually involves an interdisciplinary approach and means to enable the realization of successful systems. So, again there are multiple disciplines involved in this, that is why it is an interdisciplinary approach and means to enable the realization of successful systems. It focuses on defining customer needs and required functionality early in the development cycle, documenting requirements, then proceeding with design synthesis and system validation while considering the complete problem. That is the most important aspect of system design. It focuses on defining customer needs in a very early stage. So, even before we really start the design process, it looks at the customer requirements at a very early stage, and then document these requirements and try to identify the origin of these requirements, look at the grassroots level requirement and then try to design for the problem, and document these requirements in a proper way, a systematic way of documenting the requirements, and then designing the system to meet these requirements in terms of the functions and the physical architectures, and then doing the synthesis to see whether we can improve the system design, how do we optimize the system design, how do we actually have a proper trade off in the design, and then finally verifying the system to see whether it actually meets the customer requirement. And at every time we will be actually having the whole system as a focus, and every stage will be focusing on that particular aspect and keeping the whole system as in the focus, so that we ensure that once we have the whole system designed, or when we have this system designed, it actually meets the intended goals of the stakeholders. So, that is the main focus in the engineering system design. So here we actually consider the complete problem as in the initial stage itself, and then start designing from the fundamental, from the basic customer requirement, and then proceed with the system synthesis, design synthesis, and then deliver the product to meet the customer requirement. That is basically the systems engineering. So we have engineered the system to meet the customer requirement, and for that we need to have follow a particular procedure, or we need to have a systematic procedure, and this procedure basically which actually ensures that the system delivers the required functionalities. That is the systems engineering approach. You can see how this actually system engineering basically adds value into the enterprises. You know that the profitability of an engineering firm or a enterprise actually depends on two things. One is the system effectiveness, how effective the system is delivering the outputs, and its cost as an independent variable. So the cost as an independent variable will come along with the effectiveness that actually ensures the profitability of a system. This is the part where the system engineers or engineering system designers are focusing on. How do we have an effective system, or how do we ensure that effectiveness of the system which we develop. So here there are two things. One is the technical effectiveness, the other one is the process efficiency. Again, technical effectiveness is the focus of the system engineers, and operation, maintenance and logistics also part of the design process. While we design the system, we may ensure that the operation, maintenance and logistics are also taken into account, because that is again a life cycle of the system, that also taken into account when we design the system. And in this technical effectiveness there are two things. One is the performance, that is the functional performance, the requirements and the priorities. How do we actually define the functions or design the functions and identify the requirements, and then get the priorities of the customer. So based on the priorities we identify the requirements and then provide the functions in the system in order to provide the performance. And the other factors are inherent availability of the system, like reliability, maintainability and supportability of the system. So while we design the system, we ensure that the reliability and maintainability as well as the supportability is also built into the system, so that actually it ensures the inherent availability of the system, and combine this inherent availability and performance provide you the technical effectiveness, and the technical effectiveness along with the process efficiency ensures the system effectiveness. So the role of system engineers are basically to ensure that the system is effective and it actually adds value to the enterprises, and that actually leads to the profitability of the whole system. So what are the roles of system engineering in product development? So it actually integrates the technical effort across the development project. As you can see, there are different functional disciplines, there are different technological domains, and there are specialty concerns. So you look at the functional disciplines, you can see there are mechanical engineering, electrical engineering, chemical engineering, and all kinds of all the domains you need, because we need to integrate, or we need the expertise of from different disciplines, and then different domains like safety, reliability, maintainability, environment and producibility. And we have the specialty concerns like avionics, computers, communications, structures and processes. So it integrates all these technical efforts so to provide the effective development of the system. The basic building blocks of the system engineering, as you know that the mathematics and physical sciences, that is the one of the basic building block, where we do the qualitative modeling, quantitative modeling, physical modeling, theory of constraint, physical laws. So these are the based on the physical, mathematical and physical sciences, one of the building blocks of system engineering. But apart from that, we have these management sciences, where the economics, organizational design, business decision analysis and operation research are also part of the building block, and this is actually unique to system engineering, not to other engineering disciplines or the design aspects. The management sciences are very unique to this systems engineering. Similarly, you have other building blocks also like social sciences, where we have the multidisciplinary teamwork, organizational behavior and leadership, because systems engineering involves multiple specialties and multiple groups. Teamwork is very important and organizational behavior is also very important. So we actually try to incorporate these aspects also in the system engineering. Similarly, other building blocks are body of knowledge like problem definition, system boundaries, objectives, concept of operations, originating requirements. Then concurrent engineering, system life cycle phases, integration and qualification. Again, this is very unique to system engineering because definition of system boundaries, objectives, hierarchy, concept of operations are all very unique to systems engineering approach. Architectures like functional and logical architecture, physical and operational architecture, interfaces, these are again building blocks of system engineering. As well trade off like concept level trade off, risk management, key performance parameter trade off, these are also again building blocks for systems engineering. So you can see that there are multiple building blocks as I mentioned in the previous slide. There are mathematical and physical sciences, there are organizational behaviors, there are many trade off, there are many design principles like problem definition, the boundary system boundary definition, then functional architecture development, then trade off. So all these are very essential for the system engineering, and some of these are very unique to system engineering also. It cannot be seen in many other engineering fields, but in system engineering we may be using many of these as very unique in the development, and they are actually very crucial to the success of a successful system design. And some other considerations are basically achieving a balance between the inherent conflicts. So there may be many conflicts in the engineering system design like system functionality and performance, development cost and recurring cost, as I told you about the trade off. So again it is a balance between the conflict, there is a conflict of cost and development cost and recurring cost. So we need to decide which one need to have a trade off. Then the development schedule, that is time to market, again you want to do it at as early as possible, but then there are inherent risk involved in that one. Then similarly the development risk like probability of success of the whole system, especially the technological risk will be there, market risk will be there. Then similarly the business viability and success. So these are the considerations we need to have when we design the system. So it is not only the technology, but there are many other aspects to be considered when we go for the design of a system. And then we have the system optimization. Subsystems often suboptimal to achieve best balance at system level. So since we are heavily having design of subsystems, they may not be very optimal at that stage. So we need to ensure that when these subsystems are assembled or integrated, they actually provides you a good optimization. And then ultimate system's purpose must prevail against conflicting considerations. So whatever may be your conflicting consideration, the ultimate system performance what is intended at the initial stage should be always prevail. And long term considerations may drive technical decisions. So like disposal, when we have a long term consideration for disposal, we need to the technological decisions will actually focus on this also, the long term considerations of the system. Similarly the customer interface often act as honest broker. So basically this is one of the important part, because that is the area where the customer directly interacts with the system. So that also need to be considered when we design the system. And then carries burden of educating customer on hard choices. So sometimes we may have to, the system designers may have to educate the customer on harder choices. Sometimes customer may look for another option, but we need to educate them why this particular choice is needed for the system. And then must think ahead to the next customer and next application. So it is not only for that system or that customer, we need to look at the changes happening in the market or in the technology, and the design should always focus on the next application or the next customer. And always must challenge all the requirements. So do not take all the requirements as granted. So we need to challenge the requirements and then ensure that these requirements are genuine, and then we have these requirements, the origin of these requirements are really understood, and then only we go ahead with the design of the system. Always you need to challenge these requirements and ensure that you understand that particular requirement, and the reason behind that requirement, the logic of having that requirement in the system should be completely understood. I will briefly go through the system engineering heritage and how actually the system engineering developed as a particular stream. Though the system engineering is only 100 years or so old, the traces of engineering systems can be seen even in 4000 BC. The water distribution system in Mesopotamia was in 4000 BC is an example for a system engineering, and similarly the irrigation system in Egypt, the urban systems such as Athens and Greece, Roman highway systems, water transportation systems, telephone systems in 1877 and electrical power distributions in 1880. So, these are examples for the latest or the recent ones, but you can see in BC itself, in 4000 BC itself, there were systems which actually could qualify as engineering systems. The modern origins of the systems can be found in the British multidisciplinary team formed in 1937 to analyze air defense systems. So, probably that was one of the first organized system engineering approach in the designing of some complex engineering systems. So, in 1937 British team, multidisciplinary team was formed to analyze air defense system. Then Bell Labs supported Nike development in 1939 to 1945, and Sage air defense system defined and managed by MIT in 1951 to 1980. I will see a little bit about the Sage air defense system, what are the subsystems involved in this system at a later stage. And then, as I mentioned, the Atlas ICBM project which was managed by a systems contractor Ramo Woolridge Corporation in between 1954 and 1964. After this, there was a spread of systems approach in various applications. The early proponents were the Research and Development Corporation, which was actually responsible for the development of ICBM, and then Robert McNamara, the Secretary of Defense, who actually introduced these systems engineering principles in defense systems. Similarly, there were growth in engineering citations also. In 1964 there were not many citations, but in 1966 there was 1 page citation, and then at 69 it increased to 8 pages. 1964 there were 9 universities offering systems engineering program, but now there are again it is increasing. There are a lot of people actually adapting systems engineering principles for their applications. So, the teaching of system engineering was included in 1971 DoD acquisition reforms, Department of Defense acquisition reforms. A study group chaired by David Packard, co-founder of HP, was formed to study this, and then they recommended formal training for Department of Defense program managers. And then Defense System Management College was established in 1971, and DSMC charged with teaching program managers how to direct complex projects. System engineering became a core curriculum course in most of these courses. There are a lot of publications existing available for engineering system, that US Air Force Systems Engineering Handbook, then Mills Standards, then you have US Army Field Manual, then Defense System Management College System Engineering Management Guide, and NASA's Systems Engineering Handbook 1995. The discipline is actually maturing, the system engineering discipline is maturing slowly. The explosive growth in computer power is changing the systems themselves, and consequently systems engineering as practiced over the last half century. This was commented by Rechin in July 1993. And then a steady growth in commercial computer tools that automate and improve execution of systems engineering process, and increasing worldwide reports of system engineering applications. So, you can see a increase in the worldwide reports of system engineering application, which actually shows that system engineering is actually maturing as a separate discipline. Expanding horizons, collaboration with other technical societies are taking place. There are many standards being developed for system engineering. There is an encouraging international membership for this systems engineering society, and then nurturing emerging system engineering applications. There are many applications coming up with commercial and environmental areas, and then fostering the system engineering education and research is also happening. So, these are all actually promising for the system engineering to mature as a separate discipline. There are many standards existing in course, that is the International Council for System Engineering. So, there are current system engineering standards by Electronic Industries Association, then IEEE standards are there. Then we have the system engineering standards under development, ISO standards, ISO SPICE, then system engineering for space systems, and IEEE P147. So, these are the standards being developed for systems engineering. There are many products available in the market. So, if you are interested to know more about this system engineering and what are the developments taking place, you can actually refer to some of these proceedings or journals, or the organization website www.incos.org. Other technical committee papers, member books and textbooks and regional conferences are available. You can actually refer to these proceedings to know more about the system engineering. Why is it relevant to India, or why do we need to learn the systems engineering? because a lot of indigenous development of defense systems are taking place in India, and these developments really need to follow the system engineering approach because they are very complex engineering systems that actually requires multiple disciplines, and there are actually multiple teams working on it. So unless we have a systems engineering approach to these projects, it is very difficult for success of the project, and therefore we need to embrace the system engineering in a big way for the success of these projects. Similarly, there are large infrastructure projects coming up in India, especially in the construction sector, highways and expressways, and there are a lot of other construction activities. We have multiple infrastructure projects in terms of power plants and other areas. So these are all very complex engineering systems, and therefore we need to follow the systems approach in order to ensure that actually it delivers on time as well as it meets the customer requirement or the stakeholders requirement. Apart from these, there are many other social projects also coming up, like the healthcare projects, education projects, then we have this unique identification project. So these are all projects with a lot of complexity. Some of them are having the engineering complexity, some of them may be having some other complexities, but most of them have multidisciplinary teams working in order to provide the desired output. So for the success of these projects, we need to ensure that we follow the principles of engineering system design and implement these principles to ensure that the projects are successful and meets the requirement. So to conclude this lecture, we discussed about the basics of systems engineering, the importance of system engineering, and why do we need to have system engineering as a separate discipline, and what are the benefits of this using the principles of engineering system in complex system design. And then we discussed about some of those success and failures of the systems, and how do we actually learn from these failures to ensure that when we have a systematic approach in the design of systems, we can ensure that the failures are minimized, and always there will be a success in the system design. And we mentioned about some of the developments took place in system engineering, and some of the projects undergoing, as well as some of the standards existing. In the next lecture, we will look at the classification of various systems, then the role of system engineers and how does the system engineers play a vital role in the design of systems, and then further to that we will look at the requirement analysis and then the 6 functions of design process. So till we meet in the next lecture, very goodbye to all of you. Thank you.